also going to be practicing some acceleration problems. So acceleration is the speeding up or slowing down of an object. So it's, in scientific terms, it's the rate that velocity changes, so the change in velocity over the change in time. So this is our equation for acceleration. It's the change, or delta v, divided by the change in time. And delta v is the final velocity minus the initial velocity, divided by the change in time, so the final time divided by the initial time. The units are in meters per second squared. So when we're looking at meters per second squared, if you have acceleration, which is the change in velocity divided by the change in time, well, velocity is measured in meters per second, and then we divide that by a time, which is measured in seconds. So acceleration is the meters per second divided by seconds, which is the same thing as saying meters per second times 1 over a second. So you have meters times 1, which is meters, and seconds times seconds, which is seconds squared. You can also see acceleration in kilometers per hour squared. It can be in any basic length unit divided by a time unit squared. And then that would be anything for acceleration, or any of those units would work for acceleration. So a length unit divided by a time unit squared. And then if we ask if it's a vector or a scalar quantity, well, if we look at the equation right here, we have velocity. We know that velocity is a vector, so it has a magnitude and a direction. So if velocity is in the equation, then that means that acceleration also has to be a vector. So acceleration is also a vector. So that means acceleration will have a direction. And usually what you'll see is that if you have a positive acceleration, you're speeding up, and that if you have a negative acceleration, you're slowing down. You will see some cases, though, where you have a negative acceleration and you're speeding up. So it still has direction, but usually what you'll find is that the negative and the positive sign indicate if it's speeding up or slowing down. So for instance, if you have an object that is falling from the sky, well, as it falls from the sky, it will speed up, but it's going in a negative direction. And that's one of those instances where you will see that it is speeding up, but it has a negative direction. So we have instantaneous and an average acceleration. So just like we had an instantaneous velocity and an average velocity, we have an instantaneous acceleration and an average acceleration. So it is pretty much just like the velocities. So with average acceleration, that is the change in velocity over some period of time. So what was the acceleration over 5 seconds, over 10 seconds? And an instantaneous acceleration will be the change in velocity at a very specific point in time. So what would be the acceleration at 2 seconds, at 5 seconds, at 6 seconds? And then with instantaneous acceleration, you'll usually be given a graph just like with instantaneous velocity, and then you can calculate it from that point. So now let's go ahead and look at some math problems that we would have to do with acceleration. So we'll use that equation that we just learned to do some math. Alright, so let's look at a few problems. This says a sprinter goes from 10 meters per second to 15 meters per second in 5 seconds. At what rate is the sprinter accelerating? So the first thing we will do is we will look to see what the problem is asking for. So in this case, it is asking for the acceleration. We know that the acceleration is equal to the change in velocity divided by the change in time, which is the same thing as Vf minus Vi divided by Tf minus Ti. Okay, and normally in the problem, it's not going to give you a final time and an initial time. It'll usually just say this much time has passed. Okay, so now let's go ahead and translate the problem. So spinner goes from 10 meters per second to 15 meters per second. So we're starting at 10 meters per second. That is our initial velocity. And then we go to 15 meters per second. So that will be our final velocity. And then we did this in 5 seconds. So the change in time is going to be 5 seconds. So now we can just plug this into the equation. All our units match, so we can just plug it in. Acceleration is unknown. That's equal to Vf, which is 15, minus 10, which is Vi. So the change in velocity is equal to the final velocity minus the initial velocity. So that's what we did here. And our delta t is 5 seconds. So now we can just go ahead and solve. So it's 5 divided by 5, which is going to be 1 meter per second squared. So what this means is that for every 1 second that passes here, my velocity changes by 1 meter per second. All right, so let's do the next one. All right, so let's look at the next problem. I am driving east at 9 meters per second. I see a deer and I stop in 5 seconds. What is my acceleration? So again, the first thing I do is say, okay, what am I looking for? I'm looking for acceleration here. I know that the acceleration is equal to the change in velocity divided by the change in time, which is the same thing as this. Final velocity minus the initial divided by Tf minus Ti. All right, and then I know that I'm driving east at 9 meters per second. So when I look at that, I know it's going to be a velocity because I have meters per second. Then I need to just know if it's the final velocity or the initial. So I'm driving east at this speed, and I see a deer and stop. So I'm initially traveling at 9 meters per second. Then my final velocity is, well, I stopped, so that's going to be 0. So this is something that is implicit. So anytime that you come to a stop, your velocity is 0 meters per second. Anytime that you start from rest, you would probably have a velocity of 0 meters per second when you start. So that's something that's implied. It's not really stated in the problem. It doesn't give you a number. Okay, so now we have 5 seconds. Well, that's my change in time. That's how long it took me to stop. So now I have Vi, I have Vf, I have delta t, everything matches. I can plug it into the problem. So acceleration is equal to Vf, which is 0 in this case, minus Vi, which is 9, and divided by 5. So that's the same thing as negative 9 divided by 5. So when I divide that, I'm going to get 1.8. So acceleration is equal to negative 1.8 meters per second squared. So what this means is that for every 1 second that passes, my speed decreases by 1.8 meters per second. Okay, so it is negative because I am slowing down in this case. All right, so let's go ahead and look at another problem. All right, so a runner starts at a velocity of 1.2 meters per second and speeds up constantly during a workout at a rate of 0.2 meters per second squared. After 25 minutes, what is the speed of the runner? Okay, so again, first thing I do, what am I looking for? So after 25 minutes, what is the speed of the runner? So it wants a velocity, and I just need to know which one. Is it the final velocity or the initial velocity? So a runner starts at a velocity of 1.2 meters per second. So if he's starting at this velocity, that is his initial. So we are looking for the final velocity because I want to know how fast the runner is going after 25 minutes. So I know that my initial velocity is 1.2 meters per second. And I have a rate of 0.2 meters per second squared. Okay, so my acceleration is equal to 0.2 meters per second squared. I know that that's my acceleration because first of all, it does say rate. I'm speeding up constantly at a rate, so that is acceleration, but also the units are meters per second squared. And then it says after 25 minutes, so my delta t in this case is 25 minutes. I know that acceleration is equal to the change in velocity, which is the same thing as Vf minus Vi, divided by delta t. All right, so I have that, but I have a problem because my velocity and acceleration are both in seconds, or meters per second. So I have to convert this to seconds. Otherwise, I will not get the correct problem or answer. So 1 minute is equal to 60 seconds. Unit that I want goes on the top, unit that I have goes on the bottom. That should be 1,500 seconds. All right, so now I can go ahead and plug it into the formula and solve. So acceleration is 0.2. My final velocity is unknown. My initial velocity is 1.2. And my delta t is 1,500. Okay, so now I need to go ahead and solve for this. All right, so 0.2 is equal to Vf minus 1.2 divided by 1,500. So the first thing I need to do, I need to get rid of the 1,500 before I can do anything else. So multiply both sides by 1,500. So I'm multiplying both sides by 1,500. That will cancel it out. I was dividing by 1,500 here, so I had to multiply to get rid of it. You always do the opposite of whatever is being done. So 0.2 times 1,500 will give me 300. I'm just moving it to the bottom here. Is equal to Vf minus 1.2. So 0.2 times 1,500 gave me 300, and that's equal to Vf minus 1.2. So now to get Vf by itself, I'm going to add 1.2 to it. Okay, so that means that Vf is equal to 300 plus 1.2, which is 301.2 meters per second. And this is actually impossible for a runner, so I guess this person must be the Flash, because a human cannot run that fast. All right, so let's look at another type of problem. And these problems are not in your note packet, or I'm not sure if they are, but I just want to make sure you have enough examples to work off of. All right, so it says determine the final speed of an electron that has an initial speed of 264 meters per second and then is decelerated uniformly in an electric field at the rate of 16 meters per second squared, or 15 seconds. So, first thing I always do, I look for what it's asking for. It says determine the final speed. So it's VF is equal to question mark. Okay, so this problem's talking about an electron and it's talking about an electric field. That's not really the important part. It says it's asking for a final speed. When it gives us information, we can still solve for this. So the other information it gives us is 264 meters per second, which is the initial velocity. It says the initial speed of this. And then it's decelerated, so it's slowing down at a constant rate. Uniformly means constantly. At a rate of 16 meters per second squared. So that is our acceleration. Except it says it's decelerating. So if it's decelerating or slowing down, it should actually be negative. So this is a negative 16 meters per second squared. And then our change in time is 15 seconds. So 15 seconds is our change in time. Okay, so we know acceleration is equal to VF minus VI, which is equal to delta t, or divided by delta t. All right, so let's go ahead and plug it in. Everything matches, so we can do that. And remember, the acceleration in this case is negative here because of the fact that it's slowing down. I'm going to show you what would have happened if you left it as a positive number. So it's negative 16 is equal to VF, which is unknown, minus VI divided by delta t, which is 15. So the first thing I need to do is I need to multiply both sides by 15. To get rid of the 15, I'm dividing it here, so I need to multiply to get rid of it. Remember, always do the opposite. Negative 16 times 15 should give you 240, so negative 240. All right, so now we have that is equal to VF minus 264. So in order to get rid of the 264, we're going to add 264 to both sides. So negative 240 plus 264 should give me 24. And that's my final velocity. So my VF is equal to 24 meters per second. If I did not change this to a negative sign, I would have had positive 240 here. And then when I solved it, I would have had 240 plus 264, which would have given me a velocity greater than my initial velocity. If you read the question carefully, it says that the electron is decelerating, which means it's slowing down. Your final velocity should be less than your initial. And that's one way that you can check to see if you've done the problem correctly. All right, so let's do one more. All right, so Larry starts running at a pace of 1 meter per second and reaches a maximum speed of 4 meters per second and was accelerating at a rate of 0.5 meters per second squared. How long did it take Larry to reach a speed of 4 meters per second? So the first thing I always do is I translate the problem. It says how long, so delta t is what I'm solving for here. Then it says that Larry is running at a pace of 1 meter per second. Okay, and he reaches a maximum speed of 4 meters per second. So these are both velocities, so now I need to decide which ones. So If he starts running at 1 meter per second, that means that's the initial, and then he reaches a maximum of 4, and then he was accelerating at a rate of 0.5. So 0.5 meters per second squared. I know this will be acceleration because it's got meters per second squared. And I know that acceleration is equal to Vf minus Vi divided by delta t. So now let's go ahead and plug it into the problem. Acceleration is 0.5. That's equal to Vf, which in this case is 4, minus 1 divided by delta t. And then also, if you reread this problem, some people get confused because it says, how long did it take Larry to reach a speed of 4 meters per second? It is simply repeating information here because it says up here it reaches a maximum speed of 4 meters per second, and then it's just asking how long did it reach to get to that speed. So make sure you're reading the problems carefully. Alright, so now I'm going to go ahead and simplify a little bit. 4 minus 1 is 3 divided by delta t. Okay, whenever I see a fraction like this, I like to get rid of it. Since delta t is in the bottom here, I'm going to multiply both sides by delta t. When I do that, this becomes 0.5 times delta t is equal to 3. Now it's much easier to see what I need to do to get delta t by itself. So I'm going to divide both sides by 0.5, and delta t is equal to 3 divided by 0.5, which should be 6, and then it's going to be seconds. Alright, so remember when you have something like this, it's hard for students sometimes to see what you need to do to solve it, so get rid of the fractions. Simplify your life. Alright, so next class we're going to be going over graphing with motion graphs, and I'll see you in class.